So what we want to add to Lambda calculus is the notion of types. Okay. So type checking of programming languages, as you know, can catch a lot of bugs. So we want to have a systematic way by which we give types to Lambda calculus terms. Now notice that I have used the term calculi. So I have used the plural instead of calculus, because there are multiple ways in which you can give types. The kind of types that you can associate with Lambda calculus terms becomes all the way from simply typed calculus to all kinds of types involving values and things like that. Okay, so the dependent types. So the types that I assign is a big important thing about this calculus. So before we start going about defining an appropriate version of type Lambda calculus, we need to be clear about few things. First, we need to have a notion of what are the types of the language. So this can be just simple types or much more complicated. Say involving polymorphism, etc., like what we saw instead. Okay. The second thing that we want to talk about is typing judgment. So what do we mean by judgment? Okay. So let E be a term in the calculus, and let tau be a type. Okay. Judgments will be of the kind will be assertions of the kind E has type tau. Okay. These are the kind of assertions that we would like to make when talking about types in this context. Okay. And the notation for this is the familiar. So judgments are written in the notation E has type tau. Okay, this is how you write. This is to just say E has type tau. Okay. So that is what we care about judgments. So the third thing that we want to talk about is that not all judgments can be kind of valid. Okay, you might make judgments which are wrong. So we need to have typing rules. So these are a set of rules which tell you what judgments you are allowed to make. Okay. And often these come with precondition. These often come with precondition, which are themselves judgments. Okay, which are themselves judgment. Okay. Now, once we have these typing rules, we can talk about two algorithmic problems. One is the type checking problem, which is given an expression or term E, and a type given an expression E and a type tau. Decide whether the judgment E has type is a valid judgment or not. Okay. So what is this valid business here? The validity comes from the typing rules. Okay. So the validity as described by the typing rules. Okay. So this is the type checking problem. Okay. So when if you are writing a compiler for this language, then when you say that something is of this type, the compiler has to check that this is indeed a valid way of giving types. And finally, we have a type inference problem. Is given an expression compute a type if possible. So this expression might be ill-typed. Okay, so there is always this thing of if possible, such that is valid. Okay, if E is ill-typed, so if it is ill-typed, that means that is if there is no tau such that E dash is valid, then report error. We need a generalization of the notion of judgments, and let me motivate why we need this generalization. Okay, so let me ask you this question: when is the judgment x has type tau valid? Okay. So clearly I cannot say anything about this unless I know what x is. Okay, we cannot decide on this without knowing x. Okay, well, we don't really need to know x, we only need to know the type of x. Okay, we need to know the type of x. Okay, types in some sense approximate values, in the sense that they give us information about what the value of this expression would be. Okay, so in general, so for terms, what we do need is that the judgment E has type tau can only be asserted under typing assumptions, under type assumptions on free variables. Okay, yeah. So only under only if we know the free variables, what the types of the free variables of E are, can we say about the type of E. Okay, clearly this is analogous to the fact that if you know the free variables value, can we know the value associated with E, right? So just like that. Remember, the types are just manifested, are kind of properties of the values. Okay, so in this context, so we have the following generalization. Okay, so the first notion that we need is type assumption. Okay, so a type assumption is a judgment of the kind x has type tau for some variable x. Okay, so judgments on the types of variable are called type assumption. Okay, so a judgment now for us would be so the generalized judgment, if you want to talk about it, it would be like this. So it will be of the form gamma turnstile E has type tau. Okay, where gamma is a set of type assumption. Okay, So gamma will say x1 has type tau 1, x2 has type tau 2. Okay, so it will be something like this. X1 has type tau 1, xn has type something like this. Okay, and the third important thing is that type checking and inference can be done only for the case when gamma is a superset of the free variables of E. Okay. And also our typing rules will talk about this generalized judgments. Okay, so we now look at typing rules and proofs. A typing rule looks like this. Okay, a series of judgments J1, J2, etc., Jn, and a conclusion J. Okay, here in the rule about the Ji's, that is the judgments on above the line are called the preconditions, and the judgment J is called conclusion of the rule. A concrete example of a proof rule is the following. You will see it in detail later on. It's called the application rule. Okay. What does it say? If I have the precondition that f has type tau 1 arrow tau 2 and the precondition that E has type tau 1, then I can conclude from these two preconditions that f applied on E has type tau 2. Now we talk about proofs. So fix a set of rules R1, Rk. These are your typing rules for your calculus. Okay, a proof is a sequence of judgments that satisfy two properties. Following property. An empty sequence is a proof. Okay. The second property is if J1 Jk is a proof, and if Ri is a rule with all its preconditions so if all the preconditions of Ri is already there in comma, then the sequence J1 Jn, okay, so let me use n here, J1 through Jn followed by J is also a proof where J is the conclusion of R. So every you can extend a proof by a conclusion provided its preconditions are all there. Okay. So this is what we mean by applying the rule Ri.